This presentation I'm going to run through how to do frame by frame analysis of signals. Normally when you're undertaking a signal analysis you'll do so on a frame by frame basis rather than analysing the entire signal at once, particularly when you've got long sequences of data, which is the usual case. Now the example that I'm going to do is going to involve a speech analysis. I will do an electrical signal analysis later on, but I like the speech signal examples because you can hear the result of the analysis as well. So in this demonstration I'm going to take a speaker. This is Daryl Morrill, and he has lots of YouTube videos that are very good, and they're available on YouTube, and they deal with signals and systems and digital signal processing, and I really recommend that you go look at those videos. They're very good. But what I'm going to do with Daryl's speech is analyse it and try to remove the silences in his speech, because when he delivers he pauses quite a bit in order to give the student time to keep up with them. But it's just an easy signal to analyse in lots of ways. So let's just listen to Daryl first of all.
In this video we will introduce two important signals that we use a lot in signals and systems. It's the unit step function and the delta function.
Okay, so just stop it there. And you can hear that Daryl has some pauses within his speech signal. So I have a minute of Daryl recorded, which I need to bring into Matlab in order to do my analysis. So I need to read the file into Matlab first of all. So it's located, there's the file there. I've just played it on a VLC media player. It could have been played in any media player, of course. But I'll read that into Matlab using the wav read function. So I've just copied the path to the file, and now I just copy the file name, and it's a .wav file, so .wav at the end. Okay, so there's the data read in, so IP will just be a long sequence of numbers as you're familiar with now. I'm going to plot IP so we can visualize that signal. You've already heard it. Well, you've heard the first 10 seconds or so. So I'll just stretch out this image. My computer is struggling a little bit. But you can see regions of silence when you look at this signal. So there's one region of silence that's quite obvious. There's lots of silence towards the end, and there's also silence there, looks like there, etc. So really what I want to be able to do is identify those regions of silence, and then from that I'll be able to create a signal that has no silence in it. So I'm going to zoom in on this signal because I just want to find out what a region of silence looks like. And what I'm going to do is break this signal into what I call frames, short frames, and then analyze each frame to determine whether it's silent or not silent. So let's just zoom in here first of all. Okay, so when I talk about a frame by frame analysis, let's just look at this as one example. If I was doing a frame by frame analysis on this, I'd break this signal up into frames. So a frame would be a region of samples. So maybe that's one region of samples. That's the next region of samples. So we'll call that 1, 2, and I won't bother labeling the rest. There's 3, 4, 5, 6, 7, 8, 9, etc. That's enough. But I classified this region here as being silent, so we'll just put a little correct mark. This region here, this frame here, this range of samples is not silent, so I'll just put an X against that. This frame here is not silent, neither is this one. This one looks silent, this one looks silent, this one looks silent, this one, and this one isn't, and so on. But really when I'm doing a frame by frame analysis, I'm not looking at the entire signal, I'm just looking at a small number of samples from the entire signal. And that's what I want to be able to do in Matlab. Now in order to classify silence, I just need to identify a feature of silence. So I'll just zoom out a little bit again. Okay, one more maybe. Okay, so if I just try to classify what silent is, I can see silence as it's obviously going to have a low amplitude. So let's just try to work out, well, what is silence? We might classify silence as being something less than 0.03. So a frame in which the maximum is less than, we could even go less than that again, well, we'll just say 0.03. We might classify that as being silent. Okay. Let's take another look at the entire signal and see whether we can classify any other region as being silent and see if that rule works. So I might just look at the very end. I know there was silence at the very end of that recording, and we'll see whether the rule of an amplitude being less than 0.03 will mean that it's silent. Okay, so there we go. That's the end of the signal, and that all the samples seem to be below about 0.03 except for that little anomaly there. So I want to do this in code now. What I want to do is break the signal up into frames and analyze each frame to determine whether the amplitude is less than 0.025. So we'll open up an editor, typing edit at the command line. And let's just start to write some code. So we'll just say program to remove silences from a speech recording. Okay. So step 1, break the signal into frames of we'll say 0.1 seconds. That seems like a reasonable, thinking about it, when if someone is quiet for a tenth of a second, we might classify that as silence. We probably go a little bit higher than 0.1, but we'll use 0.1 for the moment. Step 2, identify silence by finding frames with we'll call them max amplitude less than 0.03. Okay, so that's how we're going to classify silence. Create a new signal which does not contain silent frames. Okay. Okay, so that kind of outlines what it is we want to do. So step 1, I need to break it into frames of 0.1 seconds. So I need to specify the sampling frequency in order to determine what 0.1 seconds is. And the sampling frequency in this case was 22,050 samples per second, which means that the frame len in samples will be 0.1 times fs. Okay, because there's 22,050 samples per second, there will be 2,205 samples in 1/10 of a second. Well, actually, I might use a bit different variable. We'll call it frame duration, just in case I want to change this later on. Frame duration equals 0.1. Just makes it neater to have all these variables defined independently. Okay, so there's my frame len. So the number of frames that I will have will be equal to the size of the signal, which I'll call n, and that's the length of the input, and the number of frames will be then n divided by frame len. And that has to be an integer value, but so we'll round the integer value, but we'll round it down to the nearest integer. So we'll use this floor function in Matlab. Okay, so that's my number of frames. So basically I need a for loop then to iterate through each frame. Before I even get into the for loop, let's just specify how a frame will be created. We'll say if the first frame of the signal will be basically from sample number 1 up to frame len. So in this case, frame len is roughly about 200. So that specifies a range. Frame 1 will specify a range of samples from 1 up to about 200. Okay. Frame 2 would then be the input samples from frame len plus 1 up to frame len by 2. So in that case it'd be roughly sample number 201 up to sample number 400. So all the samples in that range would belong to frame 2. Now I'm saying frame len is 200, but there is an exact value up there, but or sorry, 2000 it should be, rather than 200. The next frame 3, would be frame len by 2 plus 1, all up to frame len plus by 3. Okay, so that's me creating each frame individually, which is going to take a long time if I do each frame like that. So what I'd prefer to do is create a for loop to do my frame analysis. It'll be much quicker in the long run. But in order for you to understand the for loop, just take some time to make sure you understand what each of these frames represents a moving window essentially of the data that you're analyzing. So now let's use a for loop. So for k equal to 1 up to the number of frames. Put in my end for the for loop, and the frame will be equal to the input. And I'll just write it out because I've done this quite a bit. Frame by frame analysis is a very common thing to do, but I'll run through this now in a second. So I need to specify it's the input, it's a range of input samples, so I need to specify my range. This equation here is the starting point, and frame len by k is my finishing point. So bearing in mind the examples that I just did a second ago, let's just see how this would work. The first time through the loop, k will be a value of 1, which will mean that k minus 1 will be 0, and that will be multiplied by frame len. So that means the starting point for the first frame, or the first time through the loop, this value will be 1, because this is 0, up to frame len by k. Since k is 1, it'll be from 1 up to frame len. Second time through the loop, k will have a value of 2, and then k minus 1 will be 1, so that'll be 1 by frame len plus 1, up to frame len by 2, and so on. So you can create, every time we go through the loop, we'll be extracting the next frame from the variable IP, which is our data signal. Okay, so that's the bulk of the work. Every time we go through the loop, we've extracted out a frame. The next thing I need to do is determine the maximum value. So let's create a variable called maxval. I'll just copy this comment in here. Maxval equals max of the frame. So max is a built-in function in Matlab which will determine the maximum value. And what we're really looking for is, well, we want to create a new signal. So I'm just thinking what the best thing to do is. I might create a new signal outside here first. And this just really speeds up how Matlab works if I create the variable first outside of the loop. I'll try to explain that later on, but we'll just make it the new signal equal to a sequence of zeros. That's what this zero function does. Create a sequence of zeros which is of the same length as the signal. So n here is the length of the input variable IP. And we make it that makes a column vector of zeros, and you can check that out on your own in Matlab if you want to check out how the zeros function works. Now, if the maximum value is greater than 0.03, then it's not silent. Because remember, what I want to do is get rid of the silence. So I'm going to create a new signal, and we're going to set the new signal. We're going to set the first frame of the new signal equal to the first frame of non-silence extracted from the signal IP. So let's just do that. I'm going to create a new variable called count plus 1. Set that equal to count equal to 0 outside of this function, or outside of the for loop. And what I'm going to do is say the new signal, the first frame of the new signal, and again I'm going to copy and paste code from up here. And instead of k, I'm going to call that count. Copy this. I can imagine this is a little bit confusing, but this is just very similar to this up here, except up here I'm trying to extract a frame, okay, but down here I'm trying to create a new frame, and that line of code creates a new frame, and I'm going to say it equals the current frame that we're analyzing. So let's quickly just run through what I've done there. Basically, I'm at this stage I'm extracting a frame of speech. Down here I'm identifying silence. Well, I'm actually identifying non-silent frames by finding frames with an absolute more than. That makes a bit more sense. Okay. And I'm saying if the maximum value is greater than 0.03, this frame is not silent. And what I'm doing here is I had a variable new sig up here which is just zeros at the start, but what I'm going to do is create every time I get a non-silent frame I increment this counter, and what I'm doing here is making that making a new signal in which there are only frames which have no silence. So let's just save that and see if we can run it. So I'll just call this remove silence. And we'll run it. What? Okay, that should have run. I don't have any message being displayed. I might just display the count so we can see it actually working. Okay, so there's 398 non-silent frames. And let's just plot that first of all. Plot a new figure. Plot new sig. And we should see a signal with no silences, but with a lot of zeros at the end, because remember when I created that signal, new signal, it had lots of I started off with the signal being only zeros, and then I started to create new frames with no silence in them. So I might just get rid of the last few samples. So that looks like it's about at 8.8, that's by 10 to the power of 5. So that's 880,000 samples. So new sig 880,000 up to the end, I'm just going to remove completely. So I'm just going to set it to blank. Let's try that plot new sig again, and there's the new signal. Okay, so now let's listen to the new signal without the silence.
In this video, we will introduce two important signals that we use a lot in signals and systems. It's the unit step function and the delta function. And we'll actually come to the conclusion that the delta function is extremely useful, but mathematically very strange, and in fact is not really a function, but it's useful anyway. So the unit step function is pretty easy to work with. We usually denote it by u of t, where this stands for unit step. Mathematically, we can write it as it's equal to 0 for values of t less than 0, and it's equal to 1 for values of t greater than or equal to 1. So if I graph this unit step function,
okay, so I'm just going to play the same thing then with all the silences in there.
In this video, we will introduce two important signals that we use a lot in signals and systems. It's the unit step function and the delta function. And we'll actually come to the conclusion that the delta function is extremely useful, but mathematically very strange, and in fact is not really a function, but it's useful anyway. So the unit step function is pretty easy to work with. We usually denote it by u of t, where this stands for unit step. Mathematically, we can write it as it's equal to 0 for values of t less than 0, and it's equal to 1 for values of t greater than or equal to 1. So if I graph this unit step function,
Okay, so I just played the two for comparison. I've also just worked out the lengths here of each. So the original length was 60 seconds, whereas the new one with the silence removed is down to 40 seconds. Here's the code that did it. This frame-by-frame analysis is a very common thing to do. I'll try to come up with a couple of more demonstrations for you. Thanks for your attention.